I would like to welcome you all to today's tinyML talk. My name is Altaf Khan. I'll be moderating today's session. Today, we have a very interesting speaker, Muhammad Awais bin Altaf, and he'll be talking about on-sensor tinyML implementation, advancing neuroscience through wearables. We would like to thank tinyML strategic partners for helping out in arranging these talks. And those partners include AI Zip, Analog Devices, Aeon Devices, Arduino, ARM, Deep Light, Edge Impulse, Photolab, Green Waves, Gravity, IBM, Imagimob, iTemis, Clicatech, Microsoft, Nora AI, NXP, OctoML, Prophecy, Kiexo, Qualcomm, Rexon, Renesas, SAP, Schneider Electric, Sensimal, Silicon Labs, Sony Semiconductors, ST, Stream Analyze, Synaptics, Sentient, and TDK. Our tinyML community is growing on Meetup. We have 46 groups now in 37 countries with close to 13,000 members. Similarly, you can join the tinyML community on LinkedIn. We have more than 3,000 followers and more than 3,000 members and more than 10,000 followers. You can also join tinyML's YouTube channel, where all the videos of all the tinyML talks are hosted. I would like to remind you that on the 25th, we have a tinyML Trailblazers talk, in which our guest will be Luca Veri. The tinyML Summit, along with the tinyML Research Symposium, is coming up soon, so make sure to register for it. It's an in-person event in San Francisco on March 27th. The tinyML Europe, Middle East, Africa Forum, that will be taking place on June 26th to 28th. So please register for that as well. Today's speaker is Muhammad Awais bin Altaf. He received his PhD from Master Institute of Technology in Abu Dhabi in micro system engineering and interdisciplinary studies. Currently, he's an assistant professor at Lahore University of Management Sciences, where he does research in analog and digital ICs, energy efficient applied AI, and the development of ultra-low power circuit systems for wearable biomedical applications. So over to you, Awais.
Yeah, thank you, Dr. Altaf, for the introduction, and good day to all of you. So it's nice to present my work, which I am doing for a couple of years at LUMS. So it's basically on sensor tinyML implementation, where we're going to talk about advancing neuroscience through wearable devices. All right, so this is a brief outline. I just put it a little bit brief and try to focus on the main points. And so it's talk about motivation, why we want wearable, why we want neuroscience, why we want to have these stuff, tinyML implemented on sensor. And along with that, then the challenges associated with that and the big data and then hardware, how we are going to mix and merge, and what are the challenges basically we face as a designer. And then bringing those challenges and those motivation to one of the problem, which was basically close to my heart, and that's starting with the one neuroscience problem, and then ultimately we brought it to the emotion outburst detection. So we'll briefly talk about that, the intuition, and then somehow the solution which we are working on it. And then we'll summarize my talk. What are the issues which I see, which I oversee in a couple of years, or when we do a technological advancement or we develop something, and then what are the challenges which is still we see in front of our eyes. So we'll talk about those two. So the main motivation is basically the current diagnostic system, which we see around ourselves when we go to hospital, when we have any medical emergency. What you see, what you feel is basically a motivation for me. So if you see current in-hospital devices, for example, if you have any abnormality, you have a chest pain, you go to a hospital, what the doctors do, they check your vitals. Okay, so you have a vital signs machine there. They will just check your blood pressure, temperature, heart rate. And then if you say, okay, I have a chest pain, they will say, okay, we need to record your ECG. So they will put you next to an ECG machine and record your patterns for a couple of hours. If nothing comes out, they will say, okay, you need to stay for an overnight. Same thing applies for if you have something, neurological disorders, they will tell about the EEG acquisition and they will perform the same thing. And these devices are most likely, or mostly which doctors rely are in hospital. Definitely we have some of these features available in the form of home devices, but most of them are in hospital devices. And the issues we know, hospital environment itself challenging, appointments not available, costly, limited capacity, as all of us visualize these things in front of our eyes during the COVID times, that the capacity is limited, it's operated by clinicians get sick, and then along with that, there are human errors. So definitely, there are these challenges, but we need to find a solution for that. People work on these solutions, but still, if you go back, I say all the time, if you have a time machine, go back 40, 50 years back in any hospital, most of the things, the way which are operating are the same they are operating nowadays. And the issue is what? Definitely the things got modified, they're improved, but the structure is not changed. The process is almost the same. It's a little bit faster, but it's more populated. So this is one of the biggest challenge I see in the current hospital devices. Then we also have a category of portable devices. And the portable devices we have for the sugar patient, let's say the glucometer, right? We have a pulse oximeter, you can measure your pulse rate, you can measure your heart rate, you can measure your SpO2. Then we also have those wrist blood pressure, which most of the people don't want to use, but they just use it, but they still want to tally with the analog ones. Then we have the fetal monitor. So these are some of the fetal portable devices, but definitely there are some challenges with these portable devices. You can only do few readings per day. You don't want, for example, for a glucometer to prick your finger 100 times a day or 10 times a day. Couple of times is more than enough. You don't want to do that. Enough, it's not in a sense that need-wise, enough you can't tolerate it might be. You don't want to prick your fingers. And they are not wearables. You cannot wear, you cannot do your normal life activity. You have to sit in a certain place and do, and you have to cut your other activities even for a certain amount of time. And they have limited functionality. Cost might be questionable, but it's not that much costly because we can reuse it, but still cost is one of the factor all the time, comes in all medical devices. And then comes the lab test. Very interestingly, we know that again, for any lab, any test, most of the time we have to go to a hospital to just get some blood sample done from our finger, even some like 100 ml or some sort of blood, so that some test can be done, and then it takes some time, couple of days to a couple of hours to a couple of days in a remote areas, especially if you are living in a country which is not that much advanced. So it's a time consuming, and most of the time they are invasive, and also the cost is also a bigger factor. And again, coming back to the COVID time, we all know even for a simple COVID test, we rely on those strips, but those strips are not accurate. Nobody wants to use those strips as a proof. We have to rely on some reliable laboratory. So these are all the things which are around us, and I try to work on almost all of the stuff and try to see, okay, where we can improve, where we can modify. But my main core, which I'm going to talk today, is basically on the wearable devices or somehow smart wearable devices. So I'm proposing, or I work on on-chip smart biomedical devices, so we can have benefits which we can easily see. It can reduce the physician load. Definitely will never take out the physician out of the system, but it can overall try to reduce the physician load. It can help in reducing the human error, because the less the doctors or the humans are loaded, the better they can perform, and the quick response. That's one of the benefits which we can also look into it. Definitely human error is a lot of time objectable in terms of whenever you rely on some computer program, let's say some automated system, but these are the things which will remain debatable. So we want like something normal and something abnormal can be detected automatically. And definitely there are challenges. It's not like it's a free lunch. There are challenges. It's not like one disease requirement. Every person have their own patient profile. And then along with that, whenever they have certain disease, it's acts in a different manner. So these all the things need to be taken into care when you are devising something. So you cannot make one system fits for all or one system even fit for all patients. So you need to be intelligent in doing those things. So the patient specificity is one of the biggest challenge which we face whenever we try to make something for the biomedical or the wearable systems. And the data availability. That's the biggest challenge. We all know in ML, in AI, we rely on the data and how the data we have that basically decides, first of all, how big amount of data. Second thing, that the data should be good. And we should have all labels, all normal, abnormal patterns available. So these are the challenges which we see whenever we try to make some sort of sensor, some sort of device which are going to detect some abnormality. So we face these things. So we will look into it, how we can do it. And along with that, patients not only needs the artificial intelligence, rather they need intelligent devices which just not only use artificial. So that's something which we want. And along with that, since we are talking about the wearable devices, we are talking about those devices which the person is going to wear for a longer time, for 24/7, for a week. So they should have a long life. They should have been ease for a patient to wear so he can or she can perform their normal activities, and the cost should be less. So long life meaning that the overall power consumption should be very much low. Patient ease, the small size should be there, so they should be of tiny size, and the cost should also be less. So the cost definitely, as we start working, as the things comes out, the cost naturally goes down. But initially, we have to bear a bit higher cost, but still, as compared to the lab tests or as compared to going again to the doctor visits, it can be significantly less. And there are again challenges associated with that. So the things can be unstable because now we are talking about very much small system. The efficiencies can be or efficacy can be one of the biggest challenge. So we look into these things and we see how we can at least work towards that, which was not being done for let's say a couple of decades back, was not done, but nowadays a lot or extensive research is also being done in all of these areas. So coming to the big data and the hardware and those associated challenges, because we know, okay, no, we need something that is going to combine an AI, that is going to combine ML on an hardware so that it can be worked for a longer time, but how we can proceed towards that. So there are some challenges. Before that, let's talk about the big data. So we are now living in the big data for last couple of years or last decade, that we are gathering data, not only at least in a specific one domain, but overall the data is being created, and we have exponential increase in these sensors. So that's something good, that we are having sensors that can gather the data, which is useful for certain applications, certain devices. But on the medical side, it's not that much. We still rely on most of the data that is gathered and that is collected in hospital, because the reliability is one of the biggest challenges. So that's we still have to face it. But with passage of time, as the devices, as the reliable sensors come, as those approvals go through, then we can have those data. And then how to get that data, that's also one of the biggest challenge. And then there is going to be some automatic framework required, because there's a huge amount of data. You need to first analyze it before you can use it, and you can take some meaningful or actionable information. So this is also one of the biggest thing. And significant amount of computation is required. So all the time we have bunch of people talk about the local processing or the processing on edge versus cloud processing, that you can extract the data from the sensor, you have only on the front end, and then you pass it to some off-sensor processing, even if it's a laptop, if it's a cloud, if it's mobile, and do the processing there. So we have all the time a bunch of people. I'll just talk about why I work on the local processing, or what we call wearable ones. Then the cost of communication, limited bandwidth we all the time live in the limitancy. So we need to talk about those things. And the privacy, latency, and the security, all of these things comes in action. And the applications, not only it's medical, so we have multimedia, defense, medical, or even whatever. You take the name and you find an application. So again, just going or giving a holistic view of AI. So we all want simulation of human that in AI that, okay, it can sense, it can reason, it can act and adopt. So all the features which we see in a real human we want, and that's something basically in AI. And then machine learning itself is a subset of AI, which basically learns from the previous occurrence, which adopt somehow to a new data. And so meaning what we do in these medical devices, okay, we have some previous scenarios, and then based on those, it learns and it takes a new decisions. And then neural net is basically how you can mimic your human brains, and it's a subset of neuron, it's a subset of basically an ML, how layers and neurons interact, and then the implementation itself is the deep learning, how you can implement deep learning, deep neural network architecture and those things. So these are basically going from pure algorithmic approach, how you're going to map into final hardware. So these are the things we look into these things. And then we main focus on ML because AI is like a more bigger window that might not be at the moment going into in very much pretty small hardware, which I talked about, this miniaturized and the low power one. So we want to train system which can comprehend with an unfamiliar concepts. So we have different, again, categorizations. Is it supervised learning, where you can use or train algorithm by using the label data. So you have some previous occurrence and then use them to learn if some similar pattern come again. So it can take a decision. So we normally call it supervised learning. Unsupervised learning, hidden patterns for identification, which the system is not hasn't seen before, and it should be able to see those things. And then the semi-supervised learning, mix of both above. So you combine supervised and unsupervised and have like some labeled and some pattern, and then try the tool or try the system to learn or try the system to judge on a new data. And then a new categorization is the reinforcement learning, that you just give the reward based on the desired and push the negative, which we do in the robotic sort of stuff. Again, that's a little bit, you need more, I would say, power or more area to solve those things. So in general, the classification, if we just do in terms of some algorithms or known algorithms which are around there, again, I'm not putting all, most likely, I'm just putting which we use in our system in a recent time. So the supervised learning, we have naive-Bayes, we have linear regression, SVM, KNN, random forest neural nets, all of the things which can be somehow implemented on a chip in a resource budget. We have categorization of unsupervised learning. It came in clustering, hierarchical clustering, the principal component analysis. Definitely, if you are familiar, they are a little bit more hardware consuming as compared to the one which are on the supervised learning, because in the supervised learning, most of them can be implemented on chip. Again, what I'm talking about here, I'm talking about implementing the implementation part, not the training part. Yeah, just because the training part is going to be heavy. And then the semi-supervised learning, which will learn the small label data, classify large unlabeled, and it's an iterative process, which we do in the text identification, and the reinforcement learning. So for the variable systems, we mainly talk about the supervised learning, because that somehow do our job best currently. A lot of people are currently doing also on the unsupervised learning, on the semi-supervised learning, but currently I mainly focus on the supervised learning algorithms and try to see how they can do my job with a certain accuracy which is required for an application, because these all the things are totally depending upon what is your requirements for your certain application. And now coming back to that question that we want to do an on-sensor processing, to do an off-sensor processing. We want to do cloud processing or we want to do edge processing. So the first or the biggest challenges in the wearable device is that the data is going to come in the runtime and the data is going to be huge. So we are going to acquire our data from our body, whether it's an ECG, whether it's an EEG, whether it's an EMG, whether it's a PPG, but the data, the amount of data which is going to be acquired is going to be huge. So we have to deal with enormous amount of data. So there are naturally two ways. Either you process on sensor, on chip, on that small hardware, or acquire, because you are acquiring from your body and transmit it to your laptop, to cloud for the processing part. So we did for our small analysis. On the right-hand side, it's been shown that for an EEG device, it's for the seizure detection one. So we have the, on the left-hand side of this, on this right, have a sensor where we acquire the data and from the EEG basically at a sampling rate of 4096 samples per second, and then transmitted it to some off-sensor device. And we use the low power Bluetooth transmission. Again, one can comprehend, okay, you can further reduce this wireless transmission part, but definitely, but still it will be the dominating. So it came out that, okay, the power consumption was around in the 15.2 milliwatt or in the tens of milliwatt range, let's say. And the dominating factor, the more than 99%, was the wireless transmission. You can again bring it to 90%, 85%, but still it will remain the dominating factor. And the front end and the acquisition part and the digitization, because we were transmitting just, so that was under 1% or something similar. Again, these are something, there was definitely a tolerance level based on everyone's own design. Where on the right-hand side, we have the fully on-chip system. In the fully on-chip system, the power consumption shrink down to like under 1 milliwatt. That's somehow the notion, that's something we want so that we can operate for a longer time. What we are doing here, we are implementing the acquisition part. We are also integrating the feature extraction because whenever we are going to have any device, it needs to have those certain biomarkers which are based on which the doctors or the medical practitioner take a decision. We also need to embed those features on chip because we cannot let all the data go there and then, okay, let the classifier decide, because then we need a huge amount of area. We can't do this thing. So we need to have an explicit feature extractor on chip. And those features basically takes huge amount of time, which I'm going to talk during the example part. So you need to carefully select those features, and those features are going to go into this classifier, which is again on chip. So again, I'm not talking about the training here. I'm only going to considering the implementation part. Okay, we have already trained system, and we are going to upload those parameters, and then the system is operating. And then still, whenever we have some abnormality that being detected, we need to transmit. We need to communicate to the caregiver. So we still need the wireless transmission, and then medical practitioners or doctors, they don't only want to see, okay, you are saying the patient has a, for example, abnormal ECG event at 10 a.m. They're not okay with that. They want, okay, show me where. So that you need to record that data for the ECG or, for example, for the neurology EEG pattern. So you need to also record during that time. So that's why still the Bluetooth transmission or the wireless transmission is going to be huge relatively, but it will not be as it was in the left-hand part. So that's the huge benefit, at least at this time. We quoted 27 times, but anyone can do their design. But the bottleneck will be the wireless communication is going to be the biggest player, or biggest basically the power consumption bank. So this is one of the motivations that why we want to do on-sensor processing, at least for my system which I work, but definitely for certain application where you don't have to transmit the data intermittently, you don't have to transmit the data every time. Might be the cloud processing, might be the off-sensor processing is the best option, but for the most of the application which I work in the biomedical wearable systems, somehow the on-sensor processing is an ideal situation. And this is something which work on that, okay, we learn features from an enormous amount of data, and it can assist in clinical practice. Early detection, decision-making, help in treatment, medical devices, assistance to doctor, and wearable healthcare. So my goals are ultimately to innovate those algorithms for the disease detection, not most of the time scratching from the base, rather how you can innovate those so that you can reduce their complexity, and you can tweak them for a certain specific application. So that's something we look into it. And then the hardware realization, that how you can efficiently implement on hardware, how you can tweak those basic mathematics things and try to bring them on board so where you can reduce their power or area footprint. So that's somehow I depict it, and all the time I show the example for an ECG one for the feature extraction, because that's something which we can rely most of the features. And for example, in the neuroscience, they are difficult to visualize because we don't see those patterns, but for the ECG, we can see there is a pattern PQRS, which is shown here. So there's a amplitude, there is a slope, so P wave, R wave, there's a distance between these waves. So these are the features which can go into ultimately a classifier and can basically do a respective decision, or it's a regression, so it can have some values which are being known, especially for the glucose or any other specific. So that somehow we look into the wearables system where the subject can wear that device and can perform, the person can perform the normal day activities. For example, if they're going to office, if they're going for a walk, they're going for a jog, they should do their normal activity, not they have to sit in a certain place and then they can only be tracked. And also, if you go into a certain environment to sit to have your medical test, already your results are not going to be that much accurate, or they're not going to be depicting the real situation. In order to depict or in order to get the real situation, you need to be in the real environment. That's basically the motive for me for the wearable devices. So it can also, and it will overall help the system as seen on the right hand side. So it can connect you with the doctor, connect you with the emergency, connect you with your family, with your caregivers, and at the same time provide or assist you in you doing your normal activities for most of the time. Right. So till now, I mainly talked about, okay, what are the challenges and how we need to look into those things. So now I'm going to briefly talk about one of the example which we start looking into specifically for the neurological disorders and how it turns out to be an emotion. So just a bit about the autism spectrum disorder. It's a brain development conditions where the child has difficulty in communicating, socializing, and ultimately it linger on to affecting his whole life, even the adult. And the biggest challenge is it's a spectrum of disorder. So it's not only one, so it's an amalgam of multiple disorders and it's affect differently. And what we normally say, no two cases are similar, but the common thing about all of them, they suffer. So that's the issue which we feel. And autism is very much difficult to diagnose. The reason is that we want early diagnosis. Early diagnosis means under 2 years, under 1 year. And I'm going to talk about why it's very much difficult to diagnose in that level. Late ASD detection can lead to handicapped life. Data also says supports this the same things. Early detection can lead to early intervention and can help in having an independent life. And the conventional ASD detection, what currently we don't have any defined biomarkers, meaning we don't have any medical test, at least, which can say, okay, you do this test, and if this comes out, for example, do this blood test, if this comes out and you are autistic. No, it doesn't say this thing. So you need to have certain ways to figure it out, and that lingers on and that affects this early intervention. That's something which I got to know when I start diving into the topic. So that we can't do as a technological atom at this moment. Why the thing is that we can't detect it early. So if you see the types of the ASD, again, there are some of them. They are oppositional childs. The slightest issue can provoke them. They feel no one can be trusted. They have hostile and aggressive actions. They're unfocused childs. They have difficulty in processing the information. They can easily get distracted. Along with that, they're daydreaming child. They are focused in their own fantasies. They replays in their own minds, and they try to avoid the reality. And they're also pessimistic child. They want to do their own preferred activities. They will go for their personal benefits, and they get depressed about the future. So what's the issue? Why we can't detect these? So you take any child, 4, 5, 6, 7 years old, or even a little bit bigger, or even you take an adult, you will find all of these behaviors. And even you see other types, you will find all those behaviors in your normal kids. So how you can differentiate? And that's something which we are lagging. And we don't have any medical, radiological, potential signal which can determine at an early age that, okay, or at a later age, even that the person is autistic. Mainly, we have only the behavior part. And the conventional diagnosis is child-parent interview. At an early age, again, as I mentioned, you just rely on that interview thing and the time process when it is ideal for the intervention. So you monitor behavior and it goes late. So it results in late diagnosis. Conventional treatment, that we have specialized schools, therapies to perform those things. But what we found it, or what we discussed and we figured it out, the common thing among all autistic patients, even at the later age and an early age, was the lack of emotion control. So we start looking into it. Why not we use an emotion or a negative emotion outburst at the point to break in or point to dive in, where we can go in the system and try to provide a solution to that. So that's what we were looking into it, and we start looking into the negative emotion outburst stuff. And that basically we figured it out as the autistic children goes bigger, these outburst episodes starts increasing, and ultimately, if we see the suicide attempts in ASD kids or ASD adults, the percentage is 28 or times higher as compared to the normal ones. And that somehow, when we look into it, that's something, the outburst, when you cannot process your emotions and you cannot express your emotions, and then ultimately an outburst happens, and that outburst is something which is not like controllable, some sort of stuff. So the idea is that okay, a normal person, without having any signal acquisition or EEG sort of stuff, if you are telling some activity, you are performing some learning activity, they are confused. They don't know what to do. Because they are not understanding your language. They might be more profound, they might be more knowledgeable, they have a higher level than you, but they cannot understand very much simple activity which you want to force them, which you want to tell them. So for that, if there is some feedback device, feedback recording real-time EEG data, and those sort of stuff telling that, okay, now something wrong is going to happen, you need to change your way. So that, in my opinion, can avoid this emotion outburst, assist in learning, regulate those emotions, and can be done in home environments. So variability is also required, and also can reduce the economical burden, which I shown in the previous slide. So that's the main idea which we look into it and which we try to figure it out in our system. So we try to work on different solutions on the software side, that how we can look into it, try to see different databases which are available, which are reliable. So since there was no at the start, no autistic database available, so we start looking in the emotions one, and we start, okay, how we can make this negative emotion outburst detection system. So we have this bunch of hard analog front end, which I'm not going to talk here. But this DNN or customized DNN based patient specific classification processor, which I'm going to talk briefly here regarding the feature extraction and this classifier, and then ultimately the emotion detection logic, how it's working. So this is the first basically which we previously developed, and we tried some lab testing, and then we said, okay, now we need to improve further, because if something has to go for the wearable, we need to look into a lot of aspects before we take into some sort of further preclinical trials or steps. So one of the biggest challenge which we see in more, again, these are not only specific to the autism or emotion detection, these are for the common challenges, is with the efficient channel selection. So the efficient channel selection in the wearable device is something which we normally all the time call that should be comfortable to wearer. We don't want any person to wear a device, for example, where they have to shave their head, or which is like too much prominent. So we don't want something like that. And it should be long time in wearing, and the patient comfort, both of the things are matching. So we see, okay, what are the suitable channels? Definitely you will lose some accuracy. You can't get all the time or everything, but you need to look into it. So, and also there are multiple data sets available. As I mentioned, we have to rely on the data until we make our own system and we have our own results, and then we start building on top of it. But initially, we have to rely on the publicly available data. So there's a data set that's common. So we look into it, how we can get rid of it, and we find the optimal number of channels, and so that we can maximize those scenarios. And then we see, okay, initially we looked into 8 channels. We finalized 8 channels in the first system, but then say they're still bigger. We need to further reduce the number of channels. Might be in this case, the accuracy is definitely we want as high as possible, but it's not we want to claim 90 or 100% from the start. So we want to go like a little bit a good number, but at the same time, the patient comfort is one of the biggest issue in specifically when somebody can't control his or her emotions. So then we start looking into what are the best features we can do. So we start this K-best feature, sequential forward search. The best number of features can be further dive down, and these are the number of the features, the channels, which are basically from the certain patient or certain databases, and we figure it out. Okay, these the front lobe, because that's something which we want, the temporal or the front lobe, we want to rely on them instead of shaving our head. So we ultimately cut down to these 2 for one of our system, and they can be at runtime change. So that's not the biggest thing. And once we finalize the channels, ultimately we short down to the features. As I mentioned, we can't put all the data acquiring from the sensor and just put for the classification. We need to select the best subset of those features. So best subset of those features, we tried, okay, some analytical methods, some computational, some sort of hidden trials, and then some methods we use. So we ultimately use this large scale feature extraction method, how we can find these features, because we started with the temporal, statistical, the spectral, and so all sort of features have been analyzed, and then we want to reduce the feature footprint, because the feature is one of the biggest, let's say, killer in terms of hardware implementation. It kills power, it kills area. And again, if there are multiple channels, so the things are going to be at least multiplicated accordingly. So for the negative emotion outburst and no negative emotion outburst, we came into this zero crossing and the skewness sort of features, which we relied, and somehow they work better for our solution. And we can also see from the scattered centered graph, it also shows, for example, the zero crossing, we can see some discrimination for the zero crossing in the negative emotion outburst, and also skewness and can be seen in the negative emotion and not negative emotion. There is a discrimination, and that helps us. Okay, these features work good, and we verified across multiple. There are 2 or 3 databases which are available at the moment, and we verified on those that, okay, how can we differentiate those arousal and the balance states, and we're able to do that thing for our work. And I'm also mentioning those papers where we are explicitly talking about these works, so you can look into those for any further information, or you can contact me for our discussion. Right. So these are basically, as I'm mentioning, the features or the scattered plots where it was clearly showing that, okay, we have some, not only from those analysis, but also at the end we have some benefit going towards those. And then comes the classification part. So the classification, again, I'm not going into the details how we ultimately figure it out. This is the suitable option, because I'm mainly talking about, okay, let's say we have finalized one sort of classifier, and how we are incorporating and how we are implementing on hardware. So we talk about we mention it as a customized neural network. It's not deep neural network where the features have to be. So we are basically giving the trained features some sort of stuff, and we did extensive analysis that this approach has a better classification accuracy as compared with the PCA or another approaches, or the deep neural CNN approaches. So somehow for this application, we are relying on these features. So just to show that we have ultimately 2 hidden layers. We have first input layer, then an output layer, and 2 hidden layers, and then we have a bunch of neurons. We implemented sigmoid and the ReLU as function, and then we efficiently try to implement this on a hardware as shown in the right hand side. So we use the simple pipeline approach where we can reuse the hardware and again, because the multipliers, they are most likely the floating point multipliers, the sigmoid, and the ReLU is not anything which is going to be hardware consumed, but the sigmoid function is somehow it's an exponential with an inverse. So that somehow becomes an that's a costly function. Again, talking about the floating points, it becomes a huge chunk in terms of hardware implementation. So we try to optimize its implementation. For example, these are the things which we see whenever we start looking into hardware implementation, talking about a certain application. Again, that might not be true for everything, but when we see that, okay, there's a symmetric in the sigmoid activation function across the zero, and we see, okay, well, we don't have to implement this complete chunk here. Rather, if we just implement one side, and then the other side can just be replica, so we can just change the most significant bit to from 0 to 1, and it can give us the remaining sequence too. So we implemented the right hand of this one using a lookup table approach. Along with that, some scaling shift approach. Again, the details of the implementation are explicitly in the mentioned paper, but we try to optimize. We try to implement it in an efficient way. We try to exploit some of the features which are embedded, and so that we can ultimately reduce the footprint in terms of power and area, but at the same time don't hamper the classification accuracy much. So we look into this implementation because the sigmoid function was something which was coming, and also we use for the floating point multiplier also some of the tricks so that we can efficiently implement chip. So just for the sigmoid activation function, we have, like, for example, how the computation is going to happening in the first time window t is equal to 0. Data is going to come at an input layer. So here we some multiplier and then floating point errors are going to be utilized. In the next time t is equal to 1, further some computation is going to happen, and after this multiplication and addition, the sigmoid function is going to be called, and the specific opcode is going to be governed to call the sigmoid function. And the next, for example, t time is equal to 2, again multiplication and addition, and then the ReLU function is going to be activated so that we can implement it, the ReLU function, and then at the end again multiplication and addition, and then in the next time cycle this sigmoid function is going to be operated, and then based on the final value we see that, okay, where it relies and classified accordingly. So this is the normal pattern which we have implemented, and we tried different approaches, the parallel, serial, and the pipeline, and this is something was the most efficient in our case. Yeah, just again, I'm not going into explicit detail, but I'm just showing you the overall. We did 2 versions of this chip, which I just showed you for the negative emotion outburst. The overall area for both of them was 16 millimeters square. It was not because of the design, the area limitation was because of some other factors, because we were using a little bit not the advanced mode, so we're using 180 nanometer. It was 1 volt supply power, 10.13 microjoule per classification for the energy consumption. And these are some of the front end parameters for the noise, for the total harmonic distortion, for the NEF, and we were using the 4 classes for the emotion in this work. And we try to beat the numbers at least. For example, the current work was touching 85.2. Previously in our work, even we were having 73, and even another work which was previously published, and that reached around in the mid 80s also. So we try to be on the range, but definitely there's a huge amount of the accuracy which needs to be worked on so that we can improve our numbers further. This is, I'm not showing explicitly for the autism one because still we are looking into it, but for the seizure detection, we have starting doing some of the preclinical trials in a hospital. So this is how our device, like initial version of our device look like, which it's relying ultimately on the ear one. Now we have further optimized, so these wires are not dangling anymore, but just I'm putting this picture to show, and also I'm putting the link of how of the working of this system. So this is basically, or we want the system to be as miniaturized as possible, and at the same time it should be patient comfort sort of stuff. So we're looking into further optimization of this device, and the same thing we want to do within Autism 1, because for the Autism 1 we want it to be as small as size, because we want to acquire the data at the moment. For some other neurological problems, the data is available as compared to the Autism 1. Right. So I guess that I will conclude my talk with a summary, and then we can open for any Q&A. So the whole objective is basically early diagnosis of the chronic neurological disorders, and that brings a huge amount of issues. And the idea is solving the real life health and beyond challenges, whatever the way. So for example, as I mentioned, we're starting with the solving an autism, but we figure it out. There is no direct way at the moment. We need to find out some of the ways in a different way. So we are looking into this emotion and that's negative emotion outburst stuff. And for me, when we do some technological advancement, we do something which we feel can work, but then the biggest challenge comes. We do our lab testing, but as we go into the hospital, as we start talking with even we were talking before, but once we take the final ready system from our side to the clinic, then the real challenge starts. So we are facing something similar for the seizure detection one. So we are doing the preclinical trials, but the needs of the patient, need of the doctors are a little bit tweaked. They are not concerned with, okay, you claim less than 1 millivolt, you claim this much miniaturized size. They are not bothering about their thing. They need something different. Their requirements might be which you never thought even, or which you never thought even in the discussion, and even they didn't come in the discussion. At the end, they say, okay, if you have this thing, that will be really helpful for them. So these are the things which you have done the design, you have final system ready, and then they say, okay, very small thing, and it's not software, it's a really hardware. You have to go all way back and bring those things up. So these are the challenges which basically comes in the post-lab testing. And I guess that's all of us working in related to something medical. We have to deal with these things. I guess that will bring me to the end of my talk, and I would like to acknowledge the sponsors for this work, the HEC, the Islamic Development Bank, National Center for Artificial Intelligence, and the LUMS University explicitly for providing the support and the environment to conduct the work and the research. Thank you, and I'm open for any Q&A.
Thank you very much, Awais. Wonderful. There's a question from Igas Armando. He wants to know about sensor noise reduction, because if somehow you could reduce sensor noise, you can improve reliability, you can reduce computation, you can reduce latency as well. So did you look into that the data that you're collecting before classification, do you do anything to minimize the noise in that data?
Yeah, so we do a bunch of stuff at the analog front end. So we basically definitely the data explicitly, when we talk about the EEG, the data is very much noisy, because we are acquiring the data from the scalp and we don't know what is noise and what is the real data. So we do a bunch of stuff. For example, some challenges are in the form of electrode DC offset. Then there are the amplifiers adding noise. We are talking about the very much low frequency. So we have 1/f noise. So we try to mitigate those noises. And then the movements, basically the motion movement. So we try to incorporate as much as, or try to suppress those noises. So that's why there is a the benchmark of the noise, which I was mentioning explicitly about the RTI, the integrated referred noise. So the recommended noise level should be less than 1 microvolt RMS for the desired range of, for example, for the EEG signal is 0.5 to 100 hertz. For any other application, definitely that. So we try to be under that limit, but again, that is not only enough. So we also work on some of the basic reduction methods on the digital side too, for the pre-processing at a pre-processing level. And then ultimately we also rely, since we are whatever the extent we can reduce that noises level, we reduce. And then we also, because we are making our machine learning systems learn based on those labels. So even if those are a little bit noisy, but the labels are correct, we go with that thing. But I guess to respond to the second part about the reliability, yes, the reliability is still going to be concerned. That's something which we are looking into it, and that somehow we need to work on during the post-lab testing, because during the lab testing, everything was fine. As we go into the real life environment, then the issue starts coming. And the latency reduction already at the moment, we are working on a low latency for our systems. So it's for this problem, definitely we need to wait for 1 minute, I guess, before taking a decision. But for some of the application, the decision is under 2 seconds. Dr. Altaf, I guess you are mute.
Sorry. There's a question from Kesniza Michelin. You mentioned big data and managing that big data at the edge. So how do you do that at the edge? How do you store data at the edge?
Yeah, so at the moment, we don't use any sophisticated techniques. And at the moment, we use basically during the processing time, we are not using the downsampler. So later on, we use a downsampler basically, so that we can store as much as data as possible for the later visualization. Also, we start looking into some compression techniques, how we can compress the data. But at the moment, we didn't look into much about the proper management. But that's something which we really looking forward to work on those features. But at the moment, mainly the downsampling and the basic compression techniques, we look into it so that we can reduce the amount of the data.
So let's say the couple of applications that you mentioned, what is the size of the data vector that you present to the classifier?
So for example, just give an example for the seizure case. So for the seizure case, we need basically, we give that label data of 2 seconds chunk for the seizure case. So for that one, it varies. We need to have, because the issue with the seizure case is that we don't have much seizure scenarios. So I would say for the best shot, we might have given like, I'm not talking the amount of the data, I'm talking about the amount of the chunks which we are giving. So we might have given in that like thousands of those chunks, or tens of thousands of those chunks, in a sense, the samples which we are calling. And then we will see where we get good accuracy, and then we replicate, and then we see how the system is overall working.
Okay, one final question about my side, that you implement this thing in custom silicon.
Yeah.
So if you were not doing that, if you were using discrete components, so what's the difference in terms of power consumption between the two approaches?
Yeah, so the power, there are basically multiple challenges. Power is definitely one when we are going to combine the discrete component. The other challenge which we are going to face basically is the noise level, which we just, the first question is related to that. So there is something known as CMRR, common mode rejection ratio. So that is going to be very much huge. Then the quality of signal is really going to be bad. So that is the prime factor, I would say. The power can easily might be the 10x, but definitely you can optimize it. You can do some techniques to reduce as much as possible, because some of the devices which you are going to use, there will be IP and they'll be the best in the power number. But the main benefit which we get is basically integrating everything on sensor on one chip. So to reduce the power factor, and also the area factor, and also this noise stuff.
Wonderful. Thank you very much, Dr. Awais, for this wonderful discussion. All right, let's move on with some further acknowledgements. Yeah, so again, we want to thank our strategic partners for supporting us in organizing these talks. Our executive strategic partners are Edge Impulse, Qualcomm AI Research, Sentient. Our platinum strategic partners are Deeplight, Clickatek, Renesas, Sony Semiconductor. Our gold strategic partners are Analog Devices, ARM, PhotoHub, Microsoft, NXP, Sensible, ST Microelectronics, Synaptics, and then we have a whole list of silver strategic partners. So with that, we come to the conclusion of today's presentation. I would like to thank Dr. Muhammad Awais bin Altaf for his wonderful presentation, and to all of you for attending this talk. Thank you very much. Bye-bye.